recording now. Cool. So today we have Patrick Draper from the University of Illinois. Patrick is an associate professor with a wide range of research interests that I'm not going to try and list here. But importantly for this series, he's worked on tunneling in QFT in a number of different topics in a number of different directions, from bubbles of nothing to Schwinger pair production, more recently lattice simulations of vacuum decay, and what he'll tell us about today, which is tunneling in time-dependent backgrounds. So yes, please take it away. Much looking forward to hearing it.
Thanks very much, Ali. I really appreciate it, and I appreciate you guys putting together this internationally accessible seminar series, and to everybody for making the allowance of the time change, without which I would not have been here today. So thank you for joining. So yes, the title of my talk is Tunneling with Time Dependence, and this is some work in collaboration with my students, Manthos Karadas and Hao Zhang. And as Ali kind of indicated, tunneling is this wonderful subject where you can keep coming back to it and finding new things to do in all kinds of different physical scenarios. And okay, maybe it's a bit of a biased view because I wasn't always paying attention, but it seems to me that there's been an uplift of activity in the last several years and a bunch of new ideas for how to calculate things, building new tools, making new codes, figuring out when exactly different approximations are reliable, and new interpretations of old techniques that weren't completely understood. So it's kind of a neat thing that there are still holes to be dug in the subject. But I think many people's entree to the subject comes from semiclassics and the Coleman approach. Semiclassics indeed provides a lot of intuition for how things ought to work in quantum field theory beyond the perturbative expansion around a vacuum. And so vacuum decay is perhaps one of the more interesting phenomena because it's a little bit less symmetric. It's a little bit more non-equilibrium. And in some ways, it's a little bit more relevant to the real world, probably, than various other applications. So the title of the talk is Tunneling with Time Dependence, and more specifically, what I want to talk about today is some efforts to approach semiclassics if there are time-dependent backgrounds. So this will be leading order semiclassics for the rest of the talk. And right away, one thing that you would expect we have to contend with is that when there's some explicit time dependence in your action or in your Hamiltonian, then Euclidean continuations will result in a complex action. So you'll have to deal with this in some way. Oh yeah, and there's the reference to the paper. And this is just a picture of some scenario where you might generate some effective time dependence. Maybe you're slowly rolling in some trough here on the left with the yellow arrow, and at the same time, there's a deeper trough over on the right-hand side that you're trying to tunnel to. So this will supply some effective time dependence to your tunneling potential, and you would like to know what the corrections are from that. By the way, people should just interrupt if they have questions at any point. I'm not sure whether I will actually notice the chat window, so just yell at me. I think that should be fine. If I keep this window open to the right here, can you see the whole screen? Is that okay? Is it visible?
Yes.
I've got something overlaid. Okay, looks all right. All right, good. All right. So this is stuff everybody who works on the subject knows already, but let me review it very briefly. But the classic problem is something like this asymmetric double well tunneling potential, and you have a false vacuum state on the left, some spatially homogeneous vacuum state here, and you're going to tunnel out of it. Colloquially, we say you're tunneling to the true vacuum. That may or may not be strictly true, but you're at least tunneling in the direction in field space of the true vacuum. And the technique that will get you at least the leading tunneling exponent very cheaply is to work in Euclidean signature, do a Wick rotation to complex time, and look for very symmetric saddle points. Look for the O4 invariant saddle point. And that's nice. It reduces the problem to solving this ODE here in 4 dimensions. And you just you have kind of one direction that you need to tune some initial value until you get the kind of asymptotics that you want. So this is the classic shooting problem, and it gives you a rate which on dimensional grounds is going to go like kind of the typical mass scale or the VEV maybe to the 4th. There's some slop in this, and the main thing we care about is the e to the minus s action, the Euclidean action of the solution that does what you want. This is particularly simple because O4 invariance helps you a lot. It means that you can work with ordinary differential equations instead of partial differential equations. The kind of characteristic feature of nucleation here is that you have a stationary bubble. It's or static more precisely. It's a classical bubble with 0 momentum that nucleates. And throughout the whole process, real valued fields remain real in this computation. So I will look at what amount to 2 generalizations today, only one of which is explicit time dependence. The first generalization is going to be to not do the ordinary Wick rotation, but by a rotation by some other phase. And that will prove to be useful once we understand what this means for the time independent case. And the other thing will be to consider time-dependent cases where we have some other fields that are going to be moving in some potential, and they will generate some effectively time-dependent tunneling potential for our tunneling field phi. And the complications associated with, in particular, the second one here, our O4 invariance will be broken. Both of these will involve complexified degrees of freedom, and we'll see that the final states might carry momentum. The loss of O4 invariance is a real pain. It turns our ODEs into PDEs. At best, you've got O3 symmetry now. And so I'm not going to tackle that today. I think that's an important problem. It might require some interesting numerical treatment. But to avoid that today and stick with just analytic results, I will work in the thin wall limit. So this will be effective quantum mechanical models for some collective coordinate degrees of freedom. And the importance of that is it will take us back to quantum mechanics where we can effectively work with ODEs again, and it'll be easier to solve. So I'll spend a few slides now reviewing how this reduction to an effective quantum mechanical model works for just a very simple standard time-independent Euclidean case. And then having so done, we can extend it to the case with this generalized Wick rotation, and then we'll add time dependence. So we'll go at this in stages. Okay, this is a little schematic, but roughly speaking, here is how the standard time-independent analysis goes. You start with your action for your tunneling field, and V is something like that asymmetric double well that we had before. And then you do a Born-Oppenheimer approximation on it. So in the first step, you kind of neglect the very weak forces, the pressure that's provided by the asymmetry in the double well and the curvature. So you look at kind of a very large bubble as your ansatz, and you neglect curvature forces and pressure forces. And effectively what that does is it reduces your problem to a one-dimensional, 1+1 dimensional domain wall problem. So you construct first the domain wall solution, which is like your Born-Oppenheimer fast mode, and you get a domain wall profile in the asymmetric thin wall double well case. That looks like some tanh. I haven't written all the dependence here. It's just schematic. And then you go back and you write down an effective action for the slow mode, which is this very heavy lumbering wall. And it's got some collective coordinate degree of freedom for its size. So you replace the effectively what amount to the integration constants in the solution to the first stage Born-Oppenheimer problem. You replace those by time-dependent degrees of freedom, plug that back into the action, integrate over space, and you obtain an effective Lagrangian, which has this form. This thin wall effective Lagrangian captures the leading semi-classics that that you would get from a full field theory treatment. So it's nice for that purpose. You can think of the terms in this as being a kind of tension term. That's like the mass term plus some Lorentz contraction effects, and then the epsilon r cubed is the pressure effect. So if you plot for static r, for time independent r, this is some effective potential for the tunneling field, and it grows and it falls, and we're going to tunnel through this thing. So this is the Euclidean action. Is the Euclidean action? Sort of confused myself by that. Anyway, the point of this is that we have an effective quantum mechanics tunneling problem now, where we're winning back epsilon here is a positive number, and the potential is minus epsilon. So it's this is still Lorentzian. So this is going to be our picture, and the thing that nucleates is a thin wall bubble. It's got some radius. It's got some volumetric energy deficit inside, and some surface tension costs, true vacuum inside, false vacuum outside. And I want to mention that this effective model can also be used for Schwinger pair production and bubbles of nothing. All that changes is these exponents here get replaced by some dimension-dependent factor. So the problem that we're going to look at is an amplitude problem instead of a rate problem for reasons that will become apparent. So we want to think about the quantum mechanical amplitude to go from a false vacuum at some initial time ti to some state that contains a bubble of true vacuum. And I'll use a redefinition of the time coordinate always to set the final time equal to 0. That's for convenience, for reasons that we'll see. So then the e to the I s factor in the Lorentzian path integral looks like this in our effective model, and we have an integral from Ti to Tf. Now we'll do our standard Euclidean continuation, T to minus I tau. And because Tf is 0, really what this means is that we're doing an analytic continuation in Ti. Ti is getting rotated. After we do this, we now have a Euclidean path integral, and it has this effective action. Note the sign flip here and the sign flip here. And then you can just treat this with standard semiclassical methods and look for a saddle point. And we'll look for a 0 energy saddle point. We'll tune our potential so that the false vacuum has 0 energy. And this is the relevant solution. It's not an analytic solution. It stays at 0 until some time tau equal to r naught, and then it moves in a circle. So here's a plot of it as a function of Euclidean time tau. There's a plot of the bubble radius. What it does is it sits where it sits at 0 size. 0 size here, 0 size bubble means no bubble. So that means that we're in the false vacuum. And then it starts to move in the r tau plane in a circle up to the nucleation radius, which one can calculate is, in this model, it's sigma over E. So the initial time when the tunneling starts then is this minus r naught down here. And if you calculate the action of this, it scales like sigma to the 4th over epsilon cubed with a prefactor that exactly matches leading order semiclassics in the QFT. So this effective model is doing a good job, at least at the leading order, for getting the leading tunneling exponent in the thin wall limit. I want to make one technical comment here. You might be nervous about calling this a saddle point solution when it has an obvious derivative discontinuity here at -1. And what's important for this is that this is still in the domain of the action functional in technical speak, because even though the second derivative has a delta function here, this r squared that shows up in the kinetic term multiplies everything, and here r is still 0. So you have well-defined variational principle, and this is actually a stationary point of the action in the technical sense. So this calculates for us the leading contribution to the amplitude to nucleate a bubble at rest at t equals 0. All right, that's all standard stuff. Now what we're going to do is repeat the computation, but make one small tweak. We're not going to work in Euclidean signature anymore. We'll work in this kind of generalized rotation. So if gamma is minus pi over 2, we should recover the Euclidean thing, but for other values, it's something else. So we do the same operation. We look for some zero energy saddle points for which r equals 0 at some initial tau naught. And this is not exactly the analytic continuation of the previous solution, because the previous solution was not analytic. If you take it and continue it, it wanders off into the complex plane in a way that never comes back to r equals 0 at some tau naught. So we have to make an adjustment and just look for new solutions. And this is what they look like. So these are the generalized solutions. You can see it reduces for gamma equals minus pi over 2 to the Euclidean thing. And now the time when the tunneling degree of freedom starts to tunnel, or the place where it crosses 0, kind of working backwards, is r naught cosecant of gamma. So here's a plot of how they look. Now, since it goes into the complex r plane, I've plotted both the real part in blue and the imaginary part in orange of r. So r naught over here is 1. I should have normalized the numerator or the x-axis and the y-axis here. So it does something like this for some for some gamma very different from minus pi over 2. It starts very early, and it starts with a little curvature, but then moves very much in a straight line to some real value of r, which is a lot bigger than the critical point. And the imaginary part is doing something where it starts at 0 and it comes back to 0, but first it moves out a little bit into the imaginary axis. If you try and take the real-time limit of this, so gamma goes to 0, then what you find is your solutions are pushed off to tau naught goes to minus infinity. And that will be important later. All right, so we have these solutions. We can just plug them in and compute the Euclidean action. And what you find is for arbitrary values of gamma, you get the exact same tunneling exponent, exact same Euclidean action for all of them. So it's independent of gamma, same as the Euclidean answer. All right. So,
Sorry,
so
can I
we
just ask the...
Yes, please.
So is it that the real part's independent, or both the real and imaginary parts are independent of the action? Sorry, so like one of them vanishes.
Yeah. In this case, I actually don't remember. That's a good question. Definitely the real part is this, and I can't remember if the imaginary part vanishes or not. I'll get back to you on that later. We probably commented in the paper. Let's see. So, right. So we see, okay, I already mentioned that they return to the real axis up here at some r, which is outside of the critical point at r naught, where the Euclidean thing tunnels. And another thing is that they have some slope as a function of tau. So you might think, yes, they have some momentum too. They're nucleating out here, and they've got some non-zero momentum. So what does this mean? So to get some physical understanding of what this means, or give this some interpretation, let's talk about a slightly different approach to the tunneling problem using amplitudes with semiclassical wave packets. So here I want to think about just some path integral approach to calculating some semiclassical amplitude with, and what I've referred to here as semiclassical wave packets, meaning that I have in mind some kind of coherent state type wave function or some Gaussian wave packet. If you want, just think of it as the ground state of some harmonic oscillator, where the wave function can be written as some e to the is with a 1 over h bar in it. And then there will be corrections that are subleading in the small h bar limit. But what this does is it changes our path integral a little bit. So ordinarily in quantum mechanics, what we write down is the kind of Dirichlet path integral, where you fix a coordinate, usually a particle coordinate at some early time, and you fix a particle coordinate at some later time. And this is a a perfectly fine thing to do for most problems, but that's actually not good to do for tunneling problems, because in tunneling problems, it's bad to have arbitrarily uncertain initial momentum. If you have arbitrarily uncertain initial momentum, then you'll have solutions that just fly off over the barrier, that just classically go over. It's like giving a hard kick to the ball. So instead, we'll think about some type of packet solutions, and then the way that you incorporate this is to integrate over the kind of Dirichlet conditions. So we have an extra set of integrals over the initial and final position, and we weight by the wave function of the initial and final wave function. And because we've parameterized the wave function in this form, we can just absorb that into what are effectively some boundary terms in the action. So the classical action up here now has this extra stuff in it, and the definitions here are such that LC means the continued action, SC means the continued Lagrangian, and SC is the continued action. So LC has an e to the I gamma out front that would take care of this I and the Euclidean limit, and also some rotations that are happening on d tau r and explicit tau dependencies. All right, so we've rephrased the problem a little bit more generally, and the advantage of this is now we can do a slightly more general variational problem. So we can easily include boundary variations and not just fix our boundary conditions to be Dirichlet. We can have boundary variations, and then the stationary point of the action gives us two additional equations. These amount to the vanishing of the boundary variations. And what they do, they look like this. They relate the kind of bulk variation that would normally give you a surface term in integration by parts, and if you had Dirichlet conditions, that would vanish. So that is the momentum, or the continued momentum at the initial and final times, now has to be canceled off by variations of these initial and final wave functions. So what this does in the packet problem is it relates the initial and final semiclassical position and momentum to some features of the states, in particular these gradients. And these can have real and imaginary parts. So really, this is four equations. What this tells us is that if you have a semiclassical trajectory that you found by solving the equations of motion, it can also be a semiclassical approximation to certain packet amplitudes, but you may have to interpret after the fact. It's easier to just find a solution and then go back and see what wave packet states satisfy these relations. And then that tells you what wave packet problems are consistent with your solution. So for example, if I think about some kind of Gaussian wave packet for my final wave function, then the real part of PF, so that's the momentum in the tunneling trajectory, the real part of the momentum in the tunneling trajectory equals what you would have normally called the momentum in the wave packet, or the expectation value of the momentum in that wave packet. So it gives you this nice kind of map from some features of your tunneling trajectory onto the physical phase space of the semiclassical packets. Okay, so now we can go back to our solutions that we found here and try and apply this to interpret them as packet tunneling amplitudes. So the solutions for general gamma, we saw connected our false vacuum to some points outside the critical point. So here's the critical point, or the turning point of the potential. And what we actually found was some stuff out here with lower potential energy. But you can check explicitly that energy is conserved in this problem. So they still have zero classical energy. Our nucleation points still have zero classical energy. And therefore, they are actually connected by classical real-time evolution to the nucleation point of the critical bubble. They're what you would get if you nucleated the critical bubble and then let it roll for a while. It would move out here and it would pick up some kinetic energy, from rolling down in this potential. We also see that tunneling starts earlier. So this only makes sense if the parameter Ti, which was input to our problem, we wanted to know a tunneling amplitude to start in the false vacuum at Ti and end with some kind of bubble at Tf equals 0. Well, these solutions will only make sense if they fit. So we need that the Ti is less than the tau naught here where tunneling starts, these points here. All right. But tunneling is starting earlier, and it's making it through the barrier, and then it has some extra time to roll. So these solutions are taking that into account, and you can view this as gamma is trying to account for the time translation collective coordinate. Tunneling could happen in this amplitude problem. It could happen at any time. And then after it happens, the bubble should just roll. So you can check that that's what these things mean. The slope here means the classical momentum that it picked up. But we don't break the problem into two parts. We capture it all just in one go with this continued parameter gamma. Okay, maybe I should pause and see if any questions. Everybody good? Okay. All right, so now let me do something with time dependence. So go back to this picture here where we have some kind of rolling field. So this will be effectively a background field, chi, and we'll have a weak coupling to phi, so that as chi rolls, there's a small, slow change in the tunneling potential for phi. And kind of ideally, you would like to relax these restrictions of weak coupling and slow rolling. Some of them could be relaxed with numerical treatment of the problem, perhaps. But some of them are important so that it makes sense to think of phi as being in its instantaneous ground state to a good approximation. So you can't have arbitrarily violent variations of the phi potential. Otherwise, you'll start exciting it, and then you need to solve a different problem. So you can carry out this kind of Born-Oppenheimer line of attack again. I won't go through the details of that, but you can do it in a kind of combined Born-Oppenheimer and coupling expansion between phi and chi. And the upshot of it is you have the same thin wall profile for phi and a rolling solution for chi. And if you plug these things back in with their integration constant for the domain wall in phi and integrate over space, you get an effective Lagrangian, which is very similar to the one we had before. But in general now, the parameters are functions of time. This is kind of what you might expect. So our domain wall tension sigma and our energy deficit epsilon now receive some input from the functional form of chi of t. And you can go a little bit higher order here and include back reaction of the phi profile on the chi solution and so on. But this stuff is higher order, and it might be subleading to some corrections you would have to the thin wall limit. So we'll just work at this order. You can also get other corrections to the Lagrangian that don't take this form, and we'll see that a little bit later. But this is a good place to start. Okay, so now we're going to put these ingredients together. We'll work with this time-dependent effective Lagrangian and include the generalized Wick rotation. So the thing we want to do is look for some non-trivial small r solution that have a chance to connect to the r equals 0 vacuum state. We're going to look for similar pictures that we had before, where the field stays in the vacuum for a while, and then it starts to move away. And it turns out you can solve this problem and get at least the early time solutions. So they look like this. There's some solution for r that goes like the square root of tau minus tau naught. And this prefactor here eats up the dependence on the time dependence of sigma and epsilon. Here I've done a slow variation expansion. This is probably not necessary for a numerical treatment of the problem, but for any analytic treatment, it helps to do this expansion at least to some fixed order. So we'll work to linear order in changes in sigma and epsilon. They have some initial sigma naught and some velocities that parameterize how quickly they're changing. And those have gone into this prefactor C here. And then we need to figure out what is tau naught again. And we do so again by a shooting problem. So we want to shoot for solutions that will return to the real R plane at, or the real R axis at tau equals 0. Same setup as before, just slightly different initial conditions. So here's some examples. This is now the orbits instead of the trajectories in time, or the world lines, I guess. This is showing the real R on the x-axis and the imaginary part of R on the y-axis, but qualitatively it does kind of the same thing. It moves into the imaginary plane and then comes back to a variety of different real values of R that depend on the choice of gamma you have, and you can be farther and farther away from, roughly speaking, where the critical point is, although the critical point is now time dependent. And we see that our final states have kind of similar properties to before. In particular, they have some momentum, which is present even at leading order in the time dependence, same as we saw previously. Okay, so for zero velocities, so again, velocity here is changes in the domain wall tension and the energy gap. So for v equals 0, we return to a time-independent problem, and we saw you could write the action for that. Well, you can write the action for that in various ways. I don't think I wrote it in this form before, but you can write them as r cubed sigma naught or r to the 4th epsilon naught. So what we'd like to know is the first correction to that on-shell action, or its real part, in powers of these time-dependent parameters. And you can get those from the time-independent solutions. The way we've set up our variational problem is such that, as is often the case, you can get the leading correction to the on-shell action from the unperturbed solutions, but the perturbation terms in the action. And that's convenient, makes it a lot easier to deal with. So at order V, the correction that we find to the on-shell action is this, has this form. And you can kind of compare that to these forms of the unperturbed action. And this 3/4 here is indeed related to the 3 and the 4 up here. So I'll give an interpretation of this correction in just a minute. For fixed gamma, this is small compared to the leading order, as long as the variations are sufficiently slow. But if you fix the size of the variations in the parameters, or the time dependence, if you fix the magnitude of the time dependence and change gamma, you find that the result is unbounded as gamma approaches 0 or pi. So then there's a question of what gamma ought we to use for this. So here's a plot that's showing for a particular choice, gamma minus pi over 4. This is just showing that you can calculate the real part. I guess this was a case where I did this linear approximation is the dashed line, and a numerical treatment that includes all orders is this is a solid line. Okay, so how do we decide what to use for our choice of gamma? And I mentioned earlier that a constraint is that we need our starting point. It has to start tunneling sometime after the initial time that was just some input to the problem. We said, I'm going to insist that I'm in the false vacuum at some Ti. I'm going to pick that. And then I want to know what's the amplitude to have a bubble later at 0. And so we want to throw away any solutions that are starting to tunnel earlier than Ti, because that's part of our constraint. The initial state is the false vacuum. So that'll put a bound on gamma, because as we start changing gamma, as we approach the real-time axis, actually, ordinary real-time, we saw before that we're pushing the start of tunneling, this tau naught, earlier and earlier. And we're going to bound that by tau I. So we can solve that then for gamma and get rid of all the gammas and plug that in depending on the features of the time dependence. So for example, if your barrier is growing monotonically, it's getting harder and harder to tunnel through it. So you want to start earlier and earlier in order to get maximum advantage out of this. So what you should do is take gamma such that you start tunneling right away at Ti. If the barrier is growing monotonically, this is the optimal thing to do. You can plug that in, and this is the result you get. Or if it goes the other way, if the barrier is getting smaller monotonically, then it's better to start later. And the latest time you can start, consistent with the constraints, is always gamma equals minus pi over 2, the Euclidean thing. And actually, you can check that in that case, the leading order V correction vanishes. There will be higher orders than V that appear. And in more generality, you might see some competition between the different terms because you can have an energy gap that's growing and a potential barrier that's growing also, and those terms are in competition with each other. So you might have to do more work, but these are the two kinds of simplest limits where you can figure out how to optimize over gamma. The general strategy is to optimize over gamma, consistent with your constraints. So this is what you get in the case where the barrier is growing monotonically. And so if V is positive, it's favoring earlier decay. If V epsilon is positive, that's favoring later decay. But the assumption here is that this whole thing is positive. So it's lowering the action a little bit. It's trying to start tunneling earlier. So to say it another way, the precise question that this is addressing, this quantity e to the minus s, is it's not computing a rate for us, but rather an amplitude, or if you square it, a probability. Ti is the latest time when we're sure there was no bubble. And if you maximize over gamma, that's computing the leading decay probability over times up to Tf is 0. Now, if we stare at this correction a little bit, a couple of effects become apparent. So what this contains is one effect which you might have put in anyway, just by hand as a best guess. You might have thought that the best thing to do was translate your couplings back in time to the starting time Ti. If you're supposed to tunnel as soon as possible, then you need to translate your couplings back in time to Ti, and that's what this effect is doing. It's got for Ti much bigger than R naught, or much more negative than minus R naught. This thing is dominated by the Ti, and this Ti times V, or Ti times V, is exactly the linearized correction to sigma and epsilon in this form of the action here. So the leading on-shell action was that, and now if you add a slow time dependence to these, this is what this effect is doing if Ti is big. And so that dominates in that limit. But it is, we see an incomplete accounting of the order V effects, which also includes some amount of barrier evolution during the tunneling. And so this is capturing a little bit more than that, and it's not just a factor of Ti. And in the Euclidean case, one finds, I don't have a deep reason for this, but it's a result, that these effects cancel each other off. Ti equals R naught, and the linear correction to the real part of the action vanishes. There is an imaginary correction. All right, so let me just comment on what could be done with this. It is not straightforward to generalize it beyond the thin wall effect of quantum mechanics, to my knowledge. We have to solve some PDE. We have to actually get the dynamics of the bubble wall profile instead of freezing it. So we need to set up at least a two-dimensional kind of shooting problem, if you like. It's not going to be a shooting problem. It'll be some other optimization problem, but it might be possible to set it up numerically, and that would be pretty cool to try that. An intermediate thing one might do is try few parameter ansatz instead of just this one collective coordinate R. Maybe there would be some few parameter cases that would work well. But it would be, this was all at 0 temperature. It would be interesting to try and do this at with finite temperature bubble nucleation, which is of a little bit different character, and try to find some applications. I'm going to step away from that now and ask about coupling to gravity. And the reason to think about this, other than just intellectual curiosity, is that maybe the natural place to think about time-dependent vacuum decay is in the early universe. And their gravitational effects may or may not be important. The Hubble horizon was a lot smaller at early times, and maybe maybe we see more curvature in our bubble nucleation. That's possible. So we'd like to know whether or not it's something we can do, take this kind of pure QFT thing. I know this is supposed to be a tunneling and QFT talk, but I'm afraid that the back half is all about gravity. But I think there are reasons, good reasons to think about that. So we'd like to know whether we can include at least some leading gravitational effects. And so we tried 3 approaches to keep this problem as tractable as possible. I'm sure this is not exhaustive, but this is what we tried and the results. So this is not going to be a comprehensive answer to the question. So the first thing was taking rigid Minkowski space in which our tunneling was happening and changing it to something rigid that supplies the time dependence, like FRW. Another possibility is to look for an effective action for a membrane coupled to gravity. So try and do the same problem as before, but couple the domain wall itself to gravity. And a third approach, which is not so much approach as it is a, you know, when you see a type thing, is in some cases you might get some intuition from some exact solutions obtained by analytic continuation, but that certainly won't be the general case. Okay, so let me talk about each one of these. So rigid Minkowski to rigid FRW will work in the FRW slicing. So the metric looks like this, and we'll work in the slow variation limit again, so that we're not going to be strongly excited out of our ground state. So we're evolving adiabatically for the tunneling field. And that means we'll expand our scale factor to linear order in time. We could do more than that, but the assumption here is then that we have kind of small bubbles. So it would be interesting to generalize this, but to get some analytic control, let me do this expansion. So now our background spacetime is supplying the explicit factors of T. And if we expand out the action, you find that it looks like the Lagrangian for flat space plus some order H effects. You can carry out the same Born-Oppenheimer reduction, take your tunneling profile and integrate over space and get an effective action again for your bubble wall radius. And now it has these explicit factors. Oops, I don't know. For some reason it's not letting me select this. Nope. Okay, the 1 plus 3 HT out front here is now driving our time dependence of sigma. Sigma here is the time independent one. And we have some 1 plus 3 HT that's evolving the energy gap over here. And now we also have a new term. I mentioned before that this might not be the most general effective Lagrangian. And indeed, when you change the background space-time, you get extra terms at order HT, like this over here. Strangely, and again, this is not something that I have a deep understanding of, it's just a result, the order H contribution to the on-shell action vanishes. So actually that means that flat space tunneling approximations with no time dependence are better than you might have expected, at least in the H times R naught expansion, the leading correction from the time dependence appears to vanish. Next, let me try this membrane effective action story. And here we are greatly helped by some existing literature. So first, let's start with the static problem and couple the static problem to gravity for a membrane. So this is like the thin wall effective action model, but now including CDL type corrections. And the way to do it is to start with the Einstein-Hilbert action and a spherical brane. So we have the ordinary Einstein-Hilbert action, these GHY terms here at the location of the brane T. Those are converting the Einstein-Hilbert action to the first order and derivatives form. And then there's the brane tension term here. And then you can, by a process not entirely dissimilar from the previous one, convert this into an effective action for the brane radius, although you look at it and it looks bizarre and very different from the thing that I wrote before. Nonetheless, you can show with a bit of effort that it's actually equivalent to the previous, and the G Newton goes to zero limit. And this arc cinch appearing here is a trick introduced by Visser in order to write the whole thing in a first order form. So it involves some integrations by parts. These factors of F here, DST, refers to the blackening factor for the true vacuum de Sitter, and we'll assume that this is de Sitter to de Sitter tunneling. So to de Sitter vacuum, I don't have to do that. We just did that as a choice. So true vacuum de Sitter has de Sitter radius L1, false vacuum de Sitter has de Sitter radius L2, and these factors of F are just the ordinary static coordinate blackening factors. N is the lapse function with respect to a world line parameter lambda. So this is reparameterization invariant. Lambda is a world volume parameter, I should say. And so N is the lapse on that obeys this relation between the coordinate times T and R, which are T and R, T anyway is different on the two sides of the brane. All right, so this is kind of a messy effective action, but you can get the equations of motion without too much difficulty. And in fact, it turns out that the only equation of motion that matters, the only one that's not redundant, is the variation with respect to the lapse. The variation with respect to the bubble radius r gives you just the proper time derivative of the equation of motion ds dn equals 0. And pleasingly, what you find is that the equation of motion obtained from this effective action 2 here is nothing but the Israel junction condition that you would have got from the first equation 1. So we didn't really have to go through this for the static brane, but it helps us do these generalizations like the continuation to complex time and including time-dependent effects. All right, so here's the equation of motion. It's the junction condition. We fix, after we find the equation of motion, we can gauge fix n equals 1, and then lambda is the proper time on the at a fixed transverse angular coordinate. It's the proper time on the world volume of the brane. All right, so this in intuition of this equation is that the jump in the codimension 2 extrinsic curvature on the brane. So this difference here is the difference in what you might call the Brown-York quasi-local energies at the brane, and the difference in them is equal to the brane mass. So that's the intuition. The energy is changing across the brane. All right, so now we're going to run our program again. So we will, before we introduce any time dependence, we'll first do this analytic continuation, and so you can just do this the same kind of thing. We can continue the energy, and one solution to this is r equals 0. That's good. That's our vacuum. And to get the other, we can rearrange our equation of motion a little bit. Actually rearrange our energy equals 0 condition here a little bit, which is the same thing, and solve for r. So you can get the relevant solutions explicitly, and you find a very similar type of behavior that the nucleation point. So here's the solutions, and you can solve for the time that it starts tunneling. You can solve for the nucleation point, and you see that it depends on gamma. And this is the solution where it nucleates at some real radius, because we live in real space. So it reaches a real radius at some time 0. That's fixed some integration constants for us. So this is very similar to the previous, now just with the order G Newton type effects baked in. And what it tells you is physically it's the same story. We can get a whole range of solutions that parameterize different tunneling times. They get through the barrier, they start rolling. All the final states that you reach in this way are related by classical time evolution to the bubble that nucleates right at the critical point. Now we can start introducing time dependence. And one way to do that is to just make parameters time dependent by hand, but that is not systematic. We really should get them by starting with some model and then doing the Born-Oppenheimer reduction again. And that turns out to be very, very non-trivial. So the only one that could be done easily, as far as I could see, was to leave the the vacuum energies as they were. I don't know why I drew an ADS one here. Okay, assume the potential is such that these two on the left and right are both de Sitter. The only case that was easy to do is to leave those two energy densities alone, but change the barrier height. And that is effectively changing the brane mass or the brane tension. So we'll allow mu to be a function of T. That we can derive fairly straightforwardly. Others are more complicated because of the construction. The gravity makes it more complicated to do others. All right, so this is just an example, and one gets now, instead of a first order energy conservation equation like we have in static cases, you get a second order time dependent equation where the right hand side is telling you about the time dependence. So this is basically saying the change in time of the energy is given by the change in time of the brane tension. So then it's the same as before. You can follow the same procedure, do a continuation, solve the leading order case, and compute the leading correction to the action if you want. All right. So let me. Yes.
This is just to say you have, say, 5 minutes left.
Thank you. Yes, I think this is going to work out. Yeah. So I'm almost done. Okay. So I just want to mention this is a little bit off the main theme of the talk, but I do want to mention that it is possible to find some exact solutions. And here is one. So the first line here shows a Lorentzian Kaluza-Klein cosmology in some slightly funny coordinates. So let me consider first the case that T is the Kaluza-Klein circle. Typo there. So the Kaluza-Klein circle is T, then it's the ordinary KK theory in a kind of funny Milne type coordinate system. So you can rotate this part back to Minkowski. This is like a cylinder, and you could take it back to Minkowski space and extend the coordinate ranges that way. This is like the Milne patch of Minkowski. And we know that this is unstable to bubble of nothing nucleation. So the bubble of nothing does something like this. It takes the KK vacuum, which is just drawn two directions, one extended direction, one KK circle, and the Euclidean Schwarzschild gravitational instanton is a solution that describes a tear, a tear that's a non-trivial pi2 hole in space-time, and then this bubble expands out, but there's no bubble interior. It just changes topology. And this is smooth, and you can calculate the Euclidean action, and it goes like r squared, the size of the KK circle. Now, what if instead we leave T as a non-compact coordinate, but we let phi be the Kaluza-Klein circle? Then what's happening is it's a Kaluza-Klein cosmology again, but the circle is shrinking and growing with time y. It starts off at y equals minus infinity, non-compact. It shrinks to 0, and then it expands again. The singularity at y equals 0 is an annoyance, and so we'll regulate it by twisting the periodicity a little bit. So instead of taking T or phi to be the KK circle, we'll take a linear combination of them to be the KK circle. And now, if you do that, the minimum radius circle in the Milne patch is something finite. So you can think of this like a circle that's shrinking. It reaches a minimum size, and then it expands again. And the space-time can be continued to something Milne to Minkowski-like. It's not completely innocuous. We want to know if it's locally Minkowski, but globally it has issues. But what we want to know here is if there's a bubble of nothing in this cosmology. And indeed, there is. You can write down pretty easily a candidate decay product, a real metric that describes the evolution of a bubble. It describes the evolution of a hole. It looks like a growing bubble of nothing. You get it by starting with 5D Myers-Perry with one angular momentum turned on and do a triple analytic continuation. And that gives you this metric here. And it's not at all obvious what this thing is if you stare at it. Okay, it looks like a jumble of letters, but with some investigation, you can find that it contains a bubble, a spheroidal bubble, and it's expanding. And the asymptotics of it match your vacuum space-time with the appropriate periodicities. That's also important. That's why this is a decay product. The asymptotics are the same as your space, and it has a hole in it. And if you look at the bubble wall, you have a spheroid which is expanding in time. But that is the decay product. It is not the instanton. And the instanton, where we continue t back to I tau, is in fact just quasi-Euclidean. Quasi-Euclidean means that it's not real. It has some i's in the metric. And this is because Myers-Perry, like all in the Kerr family, is stationary rather than static. So you get i's in the metric. Nonetheless, you can join it smoothly onto the nucleated bubble on a hypersurface, which in this case, because we're working in Euclidean, has zero momentum. And the action recovers Witten's result if you take away the angular momentum. The action blows up in the extremal limit because the minimum size KK circle diverges. But in general, what this is saying, this solution is telling you, is the amplitude to make a jump when the bubble is when the KK circle is as small as possible. Then the geometry makes the jump to the bubble of nothing, which has the minimum cost when the circle is as small as possible. And so what this is computing is an amplitude rather than a rate. All right, that's all I wanted to say. There are various possible extensions of this that would be fun to think about. It could be applied to time-dependent Schwinger processes, cosmological settings, maybe some stuff I mentioned before about expanding in quantum field theory. I'd like to look for other exact solutions. That one is pretty contrived, and so on. But let me stop there and take questions.
Thank you very much, Patrick. Yeah, any questions in the room? Actually, just let me start off with a question while everyone thinks their own.
Sure.
So when you were doing this in the first half, or rather when you had this contour which you rotated by gamma, and then you had a time dependence, and then you had your solution and your action depended on gamma, and then you optimized over gamma in some sense, or for a fixed TI you optimized over gamma, which is in some sense like optimizing over your contour.
Yes.
Might the optimal contour be not just like a rotation of a straight line?
Yes, definitely. Yeah. So that's actually a generalization I should have written down here, that we might not. This is getting you a family of possibilities, but it might not be the only thing. I don't have anything intelligent to say about that, I don't think. Just think for a minute. Yeah, I guess there's some question of whether the path matters or only the endpoint. So really the reason we were doing that was to change the starting time of tunneling. And after that, I'm not sure how much it matters. That's a good question.